So this lesson is using the y dx notation, all right? And the learning goal is simply that, learning what do y dx means and use it. Now, it shouldn't be new because it's simply just using, we're going to derive. It's just a different notation. There's a few different notations that we can use for derivatives. This is actually a really good one. It's probably one of the most common ones that's used. We're just going to understand it, all right? Now, just a really quick recap of what derivatives are. Derivatives gives us the gradient function, all right? We make a triangle with the tangent here. And we find the rise over the run, okay? We find the rise over the run, so we got y2 minus y1, x2 minus x1, and we make this infinitely small, all right? So we make the change here infinitely small, all right? So we want to have this triangle in a situation where it's as small as possible. So we want to make this triangle infinitely small to find the accurate gradient at a point. Okay. So that's what derivatives are in the most basic level, and hopefully you understand this. Now, in maths, we use a lot of Greek, okay? So what we want to do is that we're looking at the change in y, and that's what y2 minus y1, it means change or the difference. So the Greek letter that we use normally is delta, which is the small, is the lowercase of delta that you may see like that, okay? So we want to see the change in y, change in y would be y2 over y1, and the change in x, all right? So instead of writing x1 and x2 and y1 and x2, we can write the change in y and the change in x, right? So that's where our notation comes from, okay? So, yeah, so instead of the gradient being y2 minus y1 over x2 minus x1, we find that our gradient function can be the change in y over the change in x as the limit of the change approaches 0. Okay, so we want these little triangles to be as infinitely small as can be. All right, so we can find the accurate, we can be accurate in what the gradient is. All right, so that's sort of a quick recap on why we use this notation. Now, in maths, what we've done is that we've sort of changed that little delta and we've put it into the language that we use at the moment, and we just used, instead of delta, little delta, we use dy over dx, all right? And all we do now is derive, all right? So we go 6x plus 2. Remember, the power multiplies the front and it goes down by 1. 2 minus 1 is just 1. We don't need to write that in, okay? And with this one, it just goes, the x disappears and then the constant just stays, all right? All right, let's find the derivative of this one. Well, first of all, I have to change it to indices, all right? So I've changed it to an indice. Now I can go dy dx, all right? So essentially, well, it is performing the same function as we had as f dash x, all right? So, but now we're using just a different notation, which is dy dx, and hopefully I've explained how it works. So it's going to be half times 2, which is just 1, x to the power of negative a half. I can rewrite that if I wish as 1 over root x. Okay, let's do one more question. It says find the equation to the tangent and the normal of the curve this. All right, so I'm going to use my new notation. So the first thing I want to do is find the gradient function, so I can find the gradient at this point. So I'm going to go dy dx equals 2x, and that's from here. All right. at x equals 1, because that's the x value here. That's a y value. We don't need it for the moment. The gradient will be 2, because you just sub x equals 1 into that one. All right, and it says to find an equation. Okay, so when it says to find an equation, we need to put our very important formula in, and it's called the gradient point formula, because we need a gradient and we need a point. All right. Now, luckily enough, we have found our gradient and we have our point. All right, so let's do it. So we get y minus, what's y1? Well, that's just 2, because that's the y point. Our gradient is 2 as well. X minus, what's x1? Well, it's just 1, so we go 1. And we just play around with it. So I'm going to ski jump the right-hand side. And let's put it in gradient intercept form. Seems pretty good to me. Oh, it's going to be 0. So it's just y equals 2x. So that's the tangent at this point here. All right, so that's the tangent at that point. Now the tangent of the normal, remember, we'll have, so gradient at 1, 2 is, let's call it m2 equals negative a half, all right? Because remember, for the normal, that means perpendicular. So we're going to have the negative reciprocal as our gradient, all right? So let's use the same formula, y minus 2, and instead of 2, we're going to put our new gradient, which is the negative reciprocal, and it's the same point that we're dealing with, so that's why we're putting the same numbers in. Let's work this one out. It's going to be minus a half x, and that will be positive a half. So let's just go gradient intercept. Therefore, y equals minus a half x, and it's a half plus 2, so that's going to be 5 on 2. All right, and so that's the equation of normal at 1, 2, and this one is equation of tangent at 1, 2. And that's the end of our lesson for the moment. Hopefully you understand what's going on. If not, ask in class. Peace out.